Um, Done most of the homework. Just haven't finished up 16 and 17 yet.
Okay.
So yeah, I was just gonna see where if other people had the same questions, or I think part of it is I just need to go back and remind myself um, how to prove the continuity
Yeah.
of those of the intersections between U and A in both questions.
Yeah.
And then yeah, I did talk about, I had the in the discussion board, I put a question talking about, do we need to discuss the three different cases for the pre-image of U? So for number 17, if the pre-image of U was, you know, if it was completely inside of A, or if it was completely outside of A, and then also if it was, um, partially inside and outside, or do we not need to worry about doing cases?
So in each case, right, in each case, it should still be true that the pre-image of F restricted to A of U should just be the pre-image of U however it hits A.
Yep.
Does that make sense? And so that's what you're saying your case is kind of justified to me?
Okay, so we don't have to actually write out three different cases.
Yeah, I don't. That's okay. You don't have to do that.
Okay. So in order to show that, might be going back, I think, but
you can just say it. It's kind of a set theory thing.
okay.
So I don't particularly want to like see a lot of justification for this. We could talk about it now, but I don't think it's worth like really justifying. Just so if I look at this function f restricted to a, that's only taking stuff. So f's a map from all of x that goes to y, right?
Right.
But then f restricted to a is just caring about what does f do to these guys. Does that make sense? Yeah. And so if I think about the pre-image of this set u back here under, say, all of f, sure, that's something. And like you said, maybe it's all outside of A, maybe part of it's in A, and maybe the whole thing's in A. Who knows? But in either case, though, if I just drew it like this, say,
yeah,
then the pre-image of f restricted to A of U is just this. Because it, like, if when I restrict to A, I'm ignoring everything outside of A. Does that make sense? It's like I don't want this extra stuff.
Yeah, it doesn't matter.
Okay. Yeah. So you can use that for free.
Okay, so then what we're trying to show is that that restriction of A is continuous. We know that F is continuous.
So that you know that this is. What do you know about F inverse of U, or the pre-image of U, if F's continuous and U is open?
It's also open.
So this is open, and then how do I get the subspace topology on A? Well, I take any open set in the big space, and I just intersect it with that. In other words, we kind of just get for free right here that this is open in the subspace.
Sorry, I couldn't quite see. I think it just says section of A. Okay. So you're saying that whole, the pre-image of U intersection with A, we know that that's all open?
Yeah, so I know that the subspace topology for A, right?
Yep.
I take all the stuff that I know is in the topology on X, and then I'm going to take those, so maybe I should write it this way, sorry. I know that TA is equal to stuff that looks like V intersect A, where V is open in the big topology.
Okay.
Does that make sense?
Yep.
And so what have you got? What we were trying to say is, well, you've got F inverse of U intersect A, and I'm just trying to say this has that form, right?
Right.
And so in other words, this is open
Yep.
in A. And that's all you need.
Yeah. So the whole thing is open. And then once we've shown that that is open, that's our proof, right? We showed.
Right? Yeah, you just showed that the pre-image of F restricted to A of U is open. Since this equals this.
Once we show it's open, we know that it's continuous.
Yep, yeah, because you just showed that the pre-image of any open set is open under here.
Okay.
So I don't think any of these are like terribly long or super complicated.
And I'm guessing number 16 is kind of similar too.
Oh yeah, very similar.
Okay. I might just hang around and see what other people have, but I don't think I have very many other questions right now.
For 16, one way to think of it, if I took the identity map, or I'll call it ID, and then I'll define this by, it takes X, and it just takes it to itself. Does that make sense?
Yep.
And so what are we doing in 16? We're saying that, well, what if I have maybe a subspace A, and I'm just kind of restricting the identity map to that subspace. Does that make sense?
Yeah.
Cool. But then really what I'm trying to say is this lives in like maybe a much bigger space, perhaps Y. So it's kind of a roundabout specific example related to 17. This is probably a more confusing way to think of it on second thought. I don't recommend it.
Yeah, no, the example you showed in the other video where you had you just had the
real line, and then I took it and I put it in 3 space.
Yeah, that was helpful.
Oh, good, good. Yeah.
So in that one, we're just trying to prove that the inclusion map by.
Yeah, so if I take this, the real line, and identify it with this line here, that's a continuous function. As far as like say the topologies on here go, where like maybe with this one, maybe this is R with like the usual topology, and maybe this is R3 with the usual topology on R3. They're like open balls that are 3D.
So in our general case, we're trying to show that the pre-image of U is open in A. But we've shown that U in X is open on the right side after the function times. And the pre-image is open in A. So once again, we're looking at that intersection of the pre-image between.
Yeah. So, saying suppose U is open, and you want the pre-image of U open in A.
And we basically use the same argument as we just showed in the second thing.
Yeah, that the pre-image under I of U, so like I only care about the stuff not from all of X that maybe gets mapped to U, if anything. If it's coming from I, then I know it just has to be from A. So that should just be, and in this case it's a little bit different, just because what else do I know? I know that these are like the same space X and X, right? I can think of it that way.
Yeah, so how does that change? Does that change something?
Just because I can actually say what should the pre-image of I be? Well, it should still be stuff in U. So in other words, this should kind of pull back to stuff here. So like I still got that same shape sitting here, right? That's what I'm trying to emphasize. That like this much and this is the same.
It's just going to be identical.
But then I only care about, well, what's the stuff that actually hits A? The only thing that's different is I can actually say what, you know, a little bit more about what's actually intersecting with A, because I know I of X is just itself for every X in A. Does that make sense?
Yeah. Someone had mentioned in the discussion board one of these questions that they read the notes on this section and they said something about an if and only if statement. They felt like maybe they had to go both ways.
For this one?
I don't know if it was 16 or 17.
Yeah, it was for this one.
So it should be so what should go both ways?
So the notes, they kind of.
Yeah, I should look at those. I didn't catch that.
Yeah, the notes have a hint. It says prove X is in the pre-image of U if and only if X is in the intersection of U and A.
Which notes is it? Subspaces 1, 2, or 3?
This is 3 on the 3rd page. Top.
Oh, so they're just justifying that quality. So like I don't really need you to justify it for me. So they're trying to say that X is in the pre-image under I of U. So then what does that mean? So that's the same thing as saying that I of X is actually in U, right?
Yeah.
But then how does I work?
Wouldn't that mean that X is in U?
Yeah. But then what else do you know about I? If it's in the pre-image of I is only touching stuff in A, so that where does X also have to live?
In the intersection?
Yeah. So maybe I should do this here.
Can you move that up a little?
That's what he was looking for, I think. I could be wrong. I want to say Dr. Schweizgood wrote these notes if you guys have him. It looks different. I could be wrong about that, though. It looks like his handwriting.
Very meticulous.
It is, right? It's way more meticulous than I ever get. But I mean, this is kind of why I don't really need to see this, you know. This isn't too much.
So but I'm confused then. That's basically the bulk of the proof I showed. What do I need to be showing then?
You're trying to show me that this is open in A, right?
Okay.
And then, well, if I know that U is open in the big space, then by definition, when I intersect with A, that's open in A. So once I show that this equals this, I know this is open in the smaller space A. Does that make sense?
Yeah.
And so, I mean, you could say the bulk of the proof really is this part, but I feel like it's kind of silly.
Has it got to do with theorem 2.1?
I think theorem 2.1 is like the definition, yeah, of like what do the open sets in the subspace topology look like. Is that right?
Yeah, it talks about the subspace metric and the subset U of A is open only if there is no subset B is in X.
So that's kind of the motivation for metric spaces. And then right after that, they generalize it to any topological space with the same idea that if I've got some space X and I already know all about, say, the open sets, say U, and so say T is my topology on X and U is in T, then what if, instead of looking at all of X, what if I just looked at this part of X here, and I'll call this A? Could I still put a topology on this thing? In other words, does the topology on the big space tell me about a topology on just this subspace A? And how it works is, where do the open sets in A come from now? Well, it's all the stuff that was already open in T, so like this U, but I just want the piece that actually hits A. So that now, that's how I get all the open sets in A. In other words, that's how I get what TA is. Does that make sense?
Yeah.
So I think that theorem 2.1 is just kind of trying to inch us into this more general case. If you don't have a metric say, we can still talk about like this intersection of an open set with my particular subspace that I'm interested in, and that's how we define what it means to be open down here in the smaller set A.
So, sorry, I'm probably moving a little bit slower than you're talking. So you've got a topology, you know, the spaces inside of the topology are open. And then we get this space U.
So I'm saying U, let's say I know that U is already open in the big space X. In other words, I already know that U is in my original topology.
Yep. And then A is this subspace topology.
Yeah, so I'm just taking any subset of X that I like. I can put a topology on it in a way that relates to the original topology. Does that make sense?
Yeah, and now it's open because of this damage.
Yeah, and so TA, how do I make sense? What do I mean by I can put a topology on the smaller set A that relates to the bigger topology up here? I'll just define the smaller topology to be all my stuff that was in T just intersected with A.
Which is kind of what we did.
And that's what they're calling the relative topology.
So we did that in the homework, but we did it for some specific cases as well.
Yeah, so you guys were doing that for specific cases, exactly. And I think there's one of the homework problems is like, okay, so open also depends on, you know, what space I'm talking about. So like sets can be open in A, but not open in X. And I think that was one of the homework problems.
Yeah. Yeah. 7. Yeah.
So they're related in a way, but at the same time, I can't just jump from, oh, if it's open down here, then it's open up here. That's not true. Yeah, I think, like you said, that was number 7.
Okay. I don't think I have any other questions, so I might just kind of get working on this before the deadline. Thanks a lot for that.
Cool. Perfect. Have a good night or day.
Yeah, thanks. Yeah.
See ya. Robert and Susie, you got other questions about stuff?
I'm good right now. Thank you.
Okay, sure.
I'll go back, and I noticed on one of your last videos you started working out number 7, so I won't take up much time with that. But I've been trying to work on 17. I know you just kind of discussed it a little bit, but can we review that one just again real quick?
Yeah, of course. So like, let's see, 17, I go from X, and I've got a function that takes me from all of X to Y, say, right?
Okay.
But what if I don't want to take every point in X and run it through F to take me to Y? What if I only want to apply F to the stuff that lives in here? Does that make sense?
Okay.
So like when they say it's a restriction, they mean like they're restricting the domain. Does that make sense?
Okay.
And so how I'll denote that, if I wanted to go just from here to over here now, I'm going to rename it F with this bar and this A. And so it says, do the same thing that F did, but you're only applying it to the stuff that lives in here now, not necessarily anything in X. Does that make sense?
All right. All right.
Cool. And so like we're trying to show that if I know that F, which takes me from anywhere I want in X, if I know that this is continuous, then when I restrict it down to just this much, that should be continuous also.
Right.
And it comes down to like we were doing with the inclusion map a minute ago, where as far as like these topological spaces go, I know that I need to show that the pre-image of any open set over here in Y, when I look at the pre-image under this, it's got to be open back here still, right?
Okay. So I need a.
Just in A.
I'm sorry. Go say it again.
So I got to show that the pre-image of an open set here, when I think about the pre-image under this map, that it's got to be open back here in A.
Okay.
But then you know a little bit more than that. So if I like drew something like, oh, I don't know, let's say this is U. I should have done dotted everywhere just to emphasize it's open. So let's call that U. What do you know about the pre-image of U under the whole map, F, or the big map?
It's continuous.
So you know F's continuous, so you know that pre-image of U just under F without any of this restriction stuff is what kind of a set?
Open.
Great, cool. And then so, you know, maybe there's different things that happen. So when I just take the pre-image of U just under F, ignore this kind of smaller map right now. Like Robert and I were talking about, maybe there's different, or I'm sorry, Joel and I were talking about, it could happen that maybe the pre-image of U completely misses A, right? Or maybe it's contained inside of A, or maybe it just partially hits A. Does that make sense?
Yeah. So I remember him talking about the 3 cases.
Yeah, and you could write those down. That's fine. You don't have to for me, though. It's okay. And for everyone else watching out there, you don't have to. Just all I'm really doing, what this says is that I don't really care about what happens outside of A at all, right? I really only care about what happens in A. Does that make sense?
Yeah.
So that if I think about, okay, if I think about A intersect the pre-image of U, if it's this case, then that's the empty set, right?
Okay.
So the empty set, that's certainly in TA, that's fine. If I think about this case, what if the pre-image of U actually lands all inside of A? Well, I know that this is open, so that intersect A is just itself, which is still open. Does that make sense?
Yep.
And then the last case is, what if I'm here, if I'm just restricting to plugging in points from A, then I really only care about this much of it, right?
Right.
And then so again, I'm just taking my pre-image and intersecting with A. So like all the cases are just kind of justifying that pre-image of F of U, when I intersect that with A, that should be exactly the same thing I get if I just took the pre-image of the restriction map. That's kind of what those little cases were trying to justify.
Okay. Yeah. I'm following a little.
Cool. So all this restriction map says is forget about anything that's outside of A. And so if I'm going to forget about anything that's outside of A, when I take any pre-image, I better make sure that I intersect with A. That's all I'm trying to say.
Okay.
But then, like I was saying up here, this is some open set from my big top from T intersected with the subspace that I'm interested in. In other words, it's got this form, right? So kind of by definition, it's in that subspace topology.
Okay. I think it's just you and me.
Yeah.
I hate I hate when this happens.
Oh, it's all right.
All right, so that kind of makes some sense there.
Cool. And it's pretty similar to what we were doing with the inclusion map too from before. This one's kind of like a generalization that in a way.
So I kind of start off the same way. I let the pre-image of you be open, and
For which one?
number 17.
Well, that's what we were doing, right?
Yeah.
So you're going to assume you started with U open, right?
Okay. So U is open, which means the pre-image is open.
Cool. And so like, yeah, you start here, and then I'm saying we go down to here. You know that this is open because F's continuous.
Can you slide that up a little more?
Yeah. Is that a little better?
Yeah.
And then once you know that the pre-image of U under F is open, then you think about, well, what happens when I just restrict to A? So what happens when I intersect stuff with A?
It would still be open.
But now, like, open where? Open in X or just open in A? And which one do you really care about for this question?
It'd be open in A because we're restricting to A.
Right. So I only care about that it's open in A. Because I know so I guess I'm trying to say what I want to show is that this one's open, right?
Right.
And so what I'm trying to say is because I know this one's open, when I restrict to A, this is just this.
Okay.
Does that make sense?
Mm-hmm. I think I got it.
And then so this is what it means to like be open in that subspace A. Because I took a set from my topology and I intersected it with the set I'm interested in.
And that's because of that subspace topology definition.
Uh-huh. Perfect.
Okay. Cool. Hey, are you recording this?
I am.
I think last
Finally
time.
remembered.
All right.
I've started to like write a note like next to my computer so that if I look over every once in a while, I'll see it like record. Like, oh God, I forgot. So hopefully those days are behind me.
We're just human. We always forget.
Yeah.
Well, all right. Since it's just me and you want to talk about number 7?
Yeah, we can. Have you had any ideas for it so far?
Well, I need a set X. I was thinking of a small set start.
That's a good idea.
So I don't know. Would you recommend like 3 or 4 elements in there? Or?
Oh, let's try 3. Let's just try 1, 2, and 3. And then you gotta pick a topology.
All right. So I need the empty set.
Empty X.
And I need
So
other
we probably want something else in there.
Okay, so then I need a. I'm trying to think ahead of what I need. So then I need a subspace topology, or no, do I need an A?
So you need an A, you need a subspace, and so you'll just pick anything you want out of here.
All right. So,
And then from T, you'll be able to make TA.
okay.
So from T and from your choice for T and from your choice to A, that's how you make TA.
Right.
Does that make sense?
The intersections there.
Yeah. And so we should probably, like, I don't know, try to fill in maybe 1 or 2 more things here. So we should add some open sets to T.
All right. So let's say we add 1 and I don't know, 2, 3. Or did we?
Maybe let's just try 1 for right now. Let's see if that does anything.
All right. So then A. Let's say. What do I need this to equal? I need the U to be. All right. So let's say. Two, 3.
And so we want a closed set that's not closed.
Oh, close set. Okay.
Right? So like that's okay. So like right now, what are we saying the closed sets are in T? So we've still got the empty sets closed and X is closed. But then there's one more closed set, which is what?
2, 3.
Yeah. So I'm trying to pick an A so that when I when I get the subspace topology, that's not going to be 2, 3, this or this. Does that make sense how you're trying to do this?
Okay, so my subspace topology won't have the empty set or X in it?
No, it should. I'm just saying I want to try to get another closed set that doesn't have, that's not 2, 3, that's different than 2, 3.
Okay, so let's do 1, 2. So if I intersect there, I would have the empty set, I would have X, I would have 1. And I would have 2.
I think so.
All right, so
And so what are the closed sets that are in A?
all right, so my closed sets that are in A would be 3.
How come 3?
Am I thinking about that wrong?
Maybe not. So they're gonna, the closed sets in A are just complements of these now, right?
All right.
So then like
Empty
still
set.
got empty, still got X, but then what's the complement of 1?
That'd be 2, 3.
And then what's complement of 2?
That'd be 1, 3. I was looking at the wrong set.
Oh, I see.
All right, so this isn't going to work because I have 2, 3 in both closed sets.
That's okay, but do you have any closed sets that are in A that aren't closed in the big space now?
1, 3.
I think that's it.
Okay, so I need to get rid of something, correct?
Well, hold on. Like, what are we trying to show?
I'm trying to show that the intersection.
You're trying to give an example. So give an example of a space and a topology and a subspace such that you can find a set that's closed in the subspace, like 1, 3, but 1, 3 is not closed in the big space because it doesn't appear in this list. So like this is your example. You're good.
So it doesn't matter that 2, 3 is in both.
Right, because all you needed to find, could you find a closed set that's not closed in X, and 1, 3 is not closed in X.
All right.
Does that make sense?
I got a ladybug attacking me. Sorry. Yeah.
Oh.
But people who watch these videos think I'm really weird.
No. You're a Blues fan, so that makes up for everything.
Yeah, just really disappointed in our boys lately.
Yeah, they're still kind of on the edge of making it. I think they're only like 2 or 3 points out of the wild card.
They're still hovering that close.
Yeah, yeah, right.
thinking-
Despite it being how bad they are.
Yeah.
I saw something about how Bouwmeester's going to miss the rest of the season, and they're talking about he might retire, or the Blues might just buy out his contract because it's supposed to go to 2020. But he's kind of.
My friend was saying that there was talk about trading him.
Yeah, I don't think anybody would take him because his contract's so lucrative for how kind of washed up he is and how often he gets hurt.
I was shocked that they traded Stastny.
Really?
Yeah.
I was okay with it.
Really?
Yeah, I don't know.
He seemed to he never really scored a lot, but he seemed to produce and have the assist here and there.
Yeah, I think I was always disappointed because he wasn't like the star that he was in Colorado. Like that didn't translate here.
And he's working with a different offense, I guess.
Yeah. Yeah, I don't know. We'll see what happens. I heard the salary cap's going up next year, so that'll be good, I think.
That'll be interesting.
Yeah. Who knows?
It's crazy how much those guys play.
Oh, right, for how physical it is.
How many games they play, and there's some tough bastards.
Yeah. Yeah, the fact that like the playoffs go well into June, it's like summer.
Playoffs are like half the season.
Yeah, it's crazy. I mean, I think it's kind of too long. I feel like they should get rid of one of the rounds like baseball.
Yeah, probably so. They'd have more longevity in careers.
Yeah.
Probably as a result of that.
Yeah. But I don't think they'll ever change that.
Well, all right. I think I'm good. I'll have to go back and kind of read or listen over what we said about 17, but I think I got the rest of them pretty much done.
Cool.
All right. I appreciate you.
All right, bud. I'll talk to you probably Thursday or next weekend.
All right. Sounds good. Have a good one.
Take it easy.
You too.